This is John Whitaker for the Mathematical Analysis class. And this is video 1. And what I want to begin with is some proving techniques. This class is mainly going to be about proving facts, some of which we probably have seen in previous math classes. And we need to know some kind of accepted ways to logically prove facts. So for analysis, I'm going to list up about 6 proving techniques, and we're going to start with a direct proof. These are proving techniques. So a direct proof. And we can prove type of statements that we want to prove. We can prove if P happens, then Q will happen by assuming P occurs and then using algebra, known facts, and definitions logically conclude that Q occurs. So that's what we mean by direct proof. And I'd like to do an example. Okay, so as an example, let us consider proving the fact if x is greater than 0, then x squared is greater than 0. So I'm going to begin by indicating I'm proving this fact, and I'm going to do this directly by assuming the if part. So I'm going to let x be greater than 0. So for this statement to be proven, what we need to do is make sure that the statement applies. That is, we've got to be in the situation for which the statement is talking about. So x has to be something bigger than 0. What we want to show is that x squared is greater than 0. Okay, so since x is greater than 0, that means it's a positive number. And so what I'm going to do is I'm going to take this inequality and multiply both sides of this inequality by a positive number x. So what I'm going to get is that x times x will be greater than x times 0. Now I don't have to change that inequality again because I'm multiplying by a positive number x. Well, what that implies is that x squared is greater than 0. And that's what we were looking to prove. And so I'm going to indicate that we have proven what we need to do. We've shown what we needed to by putting a box here where this box will be filled in, and that indicates that we're done with the proof. Okay? The next type of proving technique I want to talk about is something called contrapositive. So we can prove, let's write down contrapositive. So we can prove if P, then Q by proving the statement If not Q, then not P. which is the contrapositive of the original statement. So it's contrapositive of if P, then Q. They're logically equivalent. So if you want to prove if P, then Q, you can do that by proving if not Q, then not P. Let's look at an example of that. Somebody might say, prove if 7 times M is an odd number, then M is an odd number. Okay, so here we're going to prove that by proving the contrapositive. So I'm indicating I'm starting on the proof. So it says if 7M is an odd number, then M had to be odd. So what we're going to prove is that if M, we will prove if M is not odd, then 7M is not odd, which is logically equivalent to the original statement. And so the way that I'm going to do that is that suppose M is not odd. Okay, in this setting, even though it wasn't explicitly stated, we're thinking that M is some kind of integer. Plus or minus whole number. So when we say M is not odd, that means that M is even. So the question might be, what does it mean to be an even number? Well, it means it's divisible by 2. So that means that M has to be a multiple of 2. So what we say is that so M has to be equal to 2 times some number. What we mean by this number is that this number is an integer. Okay. Now what we're trying to do is to show that 7M is not odd. Well, let's look at 7M. Well, 7M is going to be equal to 7 times 2k, because I'm just replacing M with 2k. And that's equal to 14k, which is equal to 2 times 7k. Well, since k is an integer, then 7k is an integer. So 7M is equal to 2 times an integer. That means it's even. Thus, 7M is not odd. That's the proof. Okay, another proving technique is proved by contradiction. So in proof by contradiction, what we're looking to do is we prove the statement if P, then Q by assuming P occurs and assuming not Q, then logically concluding an impossible I'll call it a silly statement thus the assumption of not Q is wrong, so Q must have happened. Okay, so here in the proof by contradiction, what we're doing is we have to put ourselves in a position of where the statement would apply. And we do that by assuming that P will happen. And then, so that assumption must be made. But then we're making a choice of assuming that Q didn't happen. And if Q didn't happen, we start working and come up with a statement that couldn't have occurred based on Q not happening. And so, since Q not happening leads to something that's an impossibility, our assumption that Q didn't happen is wrong. And so Q had to have happened. Let's look at an example of that. So as an example, let's prove if x is greater than 0, then 1 over x is greater than 0. Let's prove that. So here we're going to do the proof, and I'm going to indicate to the readers that I'm doing it by contradiction. It's always good to let people know what you're doing here, so it's easier to follow your logic. So here we're going to assume, we're going to let x be greater than 0. We're going to suppose the opposite of 1 over x being greater than 0, that is that 1 over x is less than or equal to 0. Now again, with x being greater than 0, that means that x is a positive number, and so if I take this inequality and multiply it by a positive number, it will retain the direction of the inequality. So what I get is x times 1 over x, let me write this down, will be less than or equal to x times 0. Thus, that says 1 is less than or equal to 0. Well, we know 1 is not less than or equal to 0. This is a contradiction, and here's how I'm going to symbolize contradiction. I'm going to have two arrows hit each other, coming in from opposite directions. That means this is a contradiction. So what that indicates is we didn't make a mistake logically, thus we must have made a mistake in our assumption. And so our assumption that we had option what to assume was that 1 over x was less than or equal to 0. Thus, that assumption is wrong. So what that means is 1 over x had to be greater than 0. And that's the end of that proof. Okay. Another statement we'd like to be able to prove is if P or Q, then R, can be proven by showing, one, if P, then R, and we also have to show if Q, then R. So we're going to prove both of these statements. This proving technique can be thought of a proof by case, or proof by cases. I'd like to look at an example of that. Okay, so as an example of that, let us prove if x is a real number, then x is going to be less than or equal to the absolute value of x. Okay, so here, it may not initially look like this is a situation that matches what I've gotten as my generic statement, if P or Q, then R. Because it doesn't look like we have two situations here. But we can break down x being a real number into various cases. And I think we could be prompted to look at this statement as something we can prove by cases by recalling what does it mean to be the absolute value of x. And I'm going to write that down in just a second. But the absolute value of x, the absolute value of something is itself if that something was greater than or equal to 0. But it's minus itself if that number was negative. And so we have kind of two cases based on that. So I could think of x as either something that's bigger than or equal to 0 or x is less than 0. And that kind of gives me two cases if it's a real number. So here I'm going to start the proof by saying let x be a real number. Let us recall what I just said about the absolute value of x. The absolute value of x is defined to be equal to x if x is greater than or equal to 0, and it's minus x if x is less than 0. Okay, so that's what we have. So we will consider two cases. Case 1 will be if x is greater than or equal to 0. Then the absolute value of x will be equal to, the absolute value of x if x is greater than or equal to 0 is itself, it's just x. Okay? So what we have is that x is equal to the absolute value of x in this case. Thus, what we have is x is less than or equal to the absolute value of x. And that's what we wanted to show, and we've shown it in a particular case. Okay, so let's look at the second case. That's if x is less than 0. Then, we're trying to compare x to the absolute value of x. So let's look at the absolute value of x. What it's going to be equal to, since x is less than 0, it's going to be equal to minus x. Absolute value of a negative number is minus itself. That makes it possible. Now, here's what I want you to notice. Since x is less than 0, then minus x will be greater than 0. So I can compare x to minus x. Therefore, what we have is that minus x is going to be, I should say, is going to be less than minus x. This one's less than 0, this one's bigger than 0. So, x is less than, don't forget, in this case, minus x is equal to the absolute value of x. So we have x is less than the absolute value of x. So, in this case, what we have is x is less than or equal to the absolute value of x. If x is less than the absolute value of x, well, it's definitely less than or equal to it. And I'll write a conclusionary statement. Thus, in all possible cases, we have that x is less than or equal to the absolute value of x. That's what we're trying to show. Okay. Next thing I want to look at is a statement having to do with proving if P, then Q or R. So if we want to prove this type of statement, we can do so by breaking it into cases by noting the first situation is if Q, then the statement is true. And part 2, if not Q, then we must show R. Okay, so here's our statement. If P happened, then either Q or R happened. At least one of those happened. So we can think about proving this by saying, well, out of the possible things that could happen, Q might have happened. And if Q happened, then the original statement is true. Well, the only other option besides Q happening is Q not happening. And if Q didn't happen, for this statement to be true, R must have happened, so that's what we've got to show. Let's look at an example of this. Okay. So here, as an example, someone might say, prove if the sum of a number with itself is equal to its square, then the number is 0 or 2. So that's what we're being asked to prove in this example. And symbolically, that is, here's what we're trying to prove. If Well, a number added with itself, well, that number could be represented by x, and added to itself is 2x, equals to x squared. Then, what we want to show is that x equals to 0 or x equals to 2. Okay, well, let's go ahead and do the proof. Use the proof. Okay. So I'm going to say let 2x equal to x squared. So I'm assuming p. I didn't write that down in my listing of how we prove such a statement, but we assume p happens so that the statement applies. So suppose that 2x is equal to x squared. Okay, so what I'll say is, if x equals to 0, then the statement is true. Remember, our conclusion is that we will show x is 0 or x is equal to 2. If x is not 0, then we need to show that x equals to 2. And that's what I've got to do. All right, well, since x is different than 0, then 1 over x exists as a number. So what I can do is take that 1 over x and multiply it by each side of this quality to get that 1 over x times 2x, if this is so, should be equal to 1 over x times x squared. Essentially, I'm taking 2x equal to x squared, dividing both sides by x, because I know that x isn't 0 in this case. Thus, what that says is that 2 is equal to x, and that's what we need to show.